talk of the conference, and it's my pleasure to introduce Amihay Hanany, and his title is Coulomb branch in the moduli space of Instantons.
Yes. Thank you very much. So we came to the last talk of the
microphone.
And
Microphone.
You're not turned on, or let me see.
Can you hear me?
Yeah.
Okay. Right. So I'm going to talk about a Coulomb branch of a three-dimensional n equals 4 gauge theory. And one of the first points I'd like to make is that over the years, when mathematicians looked at a quiver theory, let's say, let's take one of the more popular ones. So they define a quiver. Most of the attention was devoted to one branch, and that's what we call the Higgs branch. And in the math literature, this looks like the hyperkähler quotient. And there are very nice results around this. But the thing is that from the point of view of physics, or from the point of view of gauge theories, whenever I have such a quiver, there are in fact two hyperkähler manifolds. And the second one is called the Coulomb branch. And for perhaps obvious reasons, there's not been much attention about the other side, the Coulomb branch, and I think it's about time to start studying such spaces in more detail. So I'd like to reach a situation where our understanding of Higgs branches, of hyperkähler quotients, or maybe I should say it the opposite way, our understanding of Coulomb branches will be as good as we understand hyperkähler quotients. So today I'm going to introduce some progress that we managed to get with understanding of Coulomb branches. And there is some nice thing about it is that you can construct new spaces. And many of them do not have a hyperkähler quotient. So here's one more motivation why these are nice spaces. So what I'm going to say today is not going to give anything about the metrics on those spaces. So this is going to be an open question. But the way I'll present it is that we know how to construct holomorphic functions on those spaces. So here's a challenge. Try to look at those new spaces and to possibly get some information about the metric. So now in Nakajima's talk, he presented many of the details from a mathematical perspective. What I will do is to give some motivation from the physics point of view and give some details about how the way we think about those spaces, in the hope that some of this will be used, or maybe some of it will be improved. So let's in fact look at this type of this particular quiver. So it's known that the Higgs branch for this quiver is the resolution of the singularity C2 mod Zn, where n is the number of nodes in the quiver, and provided that the ranks are all 1. So this is, from the point of view of gauge theory, this is a gauge theory U1 to the n with matter fields that transform according to the information which is denoted by these lines that connect the nodes. So this is a known result. In fact, the reason I wrote it as C2 mod Zn is because I'm going to look at the singular limit of these spaces. There is a resolution, an ALE space, and in fact, many times when I'll say ALE space, I will just mean the singular limit of this space. So this is a well-known result, goes back to Kornheimer, and the thing which is not so known is that the Coulomb branch of this quiver theory is the moduli space of 1 SUN. Well, if this we take this symbol n, 1 SUN instanton on C2. On C2. Okay, so and this is a point which was basically conjectured back in the mid-90s by my colleagues in Trilligator and Zyberg, and was back then we didn't have enough tools to check that this is correct. The only check was just to test dimensions, but with the tools that we have now, we could be more confident about this identification. Now, so let's try to look at this construction of a Coulomb branch. It's always a hyperkähler, and it has dimension, and I'll write the complex dimension, which is equal to twice the rank of the gauge group. So R is the rank of a gauge group, and we will denote the gauge group by G. So in this particular example, the total rank is 6, and so the dimension of the moduli space will be 12 complex 12 rank. Now, so in order to understand this, let's look at the simplest possible case where the rank is 1, and we will take the gauge theory to be very simple. I'll just take but you still heard me in the back. I have a soft voice.
We're running out of power.
I see.
Or you're running out of charge.
Now I'll put a magnetic charge. Okay, so yeah, so let's try to understand the Coulomb branch for this case. Now the rank is 1, and since there is a classification of complex two-dimensional hyperkähler singularities, there are not too many options for the answer of this, right? So
Sorry, the C2 is a taub knot or a flat arc chord?
we don't make that distinction so much, but if you want to be picky about it, it's going to be taub knot. I mean,
It's going to be a different one.
No, I'm going to be on non-compact space in all possible directions.
Why it's not R3?
Well, there is a, we are always talking about the Coulomb branch in the infrared, and in the infrared, all directions become infinite. These are some technical details that I did not plan to go into. So it's yeah. So you could have this as a limit of some ALF spaces, but it's not going to serve the goal of the talk today. So let's leave it.
But I mean, the only Ricci flat metric that you're going to find on S1 times R3 is almost certainly going to be flat, right? So it's not, I mean, yeah, that's just going to be unique because you pass the universal cover, you've got one splitting them.
Yeah, the statement is that this Coulomb branch.
It's just that maybe it's some kind of interesting approximation of tau naught, right?
No, the Coulomb branch is the modulus space of color rather than.
Oh, I see. I see.
Okay, so I'd like to study this and to present this, and so in fact, already back in the mid-90s, people understood the Coulomb branch, and just because of uniqueness and because of symmetry, they argue that the moduli space is C2 mod Zn.
I mean, excuse me, I'm confused about the dimension. When G is SU2, rank is 1. So you get complex, you're saying dimension is.
The rank is 1 and the complex dimension is 2.
But SU2 instantons have dimension 8.
But I didn't talk about SU2 instantons. I just said that the Coulomb branch has dimension 2. Soon I will show you the moduli space of SU2 instantons, but I didn't do that yet.
Factoring out
Yeah, moduli space.
when you talk about the moduli space of instantons, you're factoring out the.
Oh, you're talking about the center. Okay, so I misunderstood.
No, I thought just Coulomb branch is the moduli space of charge 1 SUN.
Okay, yes, and there is a center. There is a center. So for SU2, there's going to be a C2 times C2 mod D2. And if you were confused about this center, then that's might be a point. But what's the?
But that's just metrically flat, right? It's just a Cartesian product. It's sort of that factor is uninteresting.
To the extent, well, I'm not going to make any claims about metrics. So I'm only going to look at the algebraic structure of these spaces. For metrics, really, I don't know what to say. Is this clear? Is this okay?
I'm still confused about the dimension C being 2R.
Yes, C2 is removed.
You choose a center. You just center
So
model.
there is the dimension here is 6 times
Okay,
2.
you remove the C2, right?
Yes, and then the moduli space is the dimension of. Okay. Now, in fact, it's a good point because when there is no framing in the quiver, there is an overall U1 which decouples, for which there is no matter charged under it. And this contributes a trivial factor of C2. Okay, so that's it's important that if I make such an identification that the Coulomb branch is given by this quiver, then there should be decoupled factors of C2, which will represent the position, the overall position of the instanton. Okay, so let's look at this case. U1 with n flavors, the moduli space is C2 mod Zn, and as an algebraic variety, it's given by a complex equation on 3 variables, x, y, and z to the n, which satisfy this relation. So what I'm going to do now is to generate the space of functions which are parameterized by x, y, and z, subject to this condition. No? So when Nakajima presented the set of these theories, he said that the classical, there's going to be a classical moduli space, which is going to be R3 cross S1. And so the Coulomb branch is this, and there's also a while group action in his computation, but here, since the group is trivial, U1, there's no while group action. But then he was saying, okay, this space receives classical corrections, which, as mathematicians, it's very hard to get. So here's the point where I will say, okay, we have some set of procedures. Where using these procedures, I will generate the quantum moduli space. So how does it go? There is an important observation in, and this is very crucial. In 3 dimensions, if you have a one form, and there is a two-form field strength valued in U1. It satisfies a Bianchi identity. And if I now define, look at this equation and define the following one form to be star of f, then I get this equation, d star j equals 0, and this is called the conservation equation. So I can think of j as an ether current, and it is a conserved current, and therefore there's going to be a conserved charge. And this charge is going to be naturally called, just because of this equation, a magnetic charge. So now this is a feature which is generic for any 3-dimensional theory, and in fact it's very special to 3 dimensions. If I will do the same trick in other dimensions, J will not be a one form, and I will not be able to assign to it a conserved current. Okay, so 3 dimension is very crucial. And so whenever I have such a quiver, and whenever I see U1, which is what I have here, I'm going to have a magnetic charge M, and by the usual quantization conditions, it's going to be a quantized magnetic charge, an integer number. So, and here's the part where I'm going to present it as a construction. It's a mathematical construction. There's some quantum corrections which are involved, but here there's no proper definition I can use. And so I'll just say that I'll construct a set of functions, and for us these are called operators, chiral operators, which are denoted by Vm. V stands for vortex, and those are called monopole operators. So this is the physical name for them, monopole operators. And as I said, what I'm going to do is to construct the set of all possible functions on this space, C2 mod Zn. So how does this come about? Well, now I recall that there is a symmetry SU2 which rotates the 3 directions over here. And this also is the symmetry that rotates the 3 complex structures on the hyperkähler singularity. And so, with respect to this SU2, I'm going to pick U1 subgroup. And so what this means that I'll just take the three complex structures, pick one of them, and define a notion of a holomorphic function with respect to this complex structure. And now I'll declare that this Vm is holomorphic with respect to this complex structure. And it will carry a representation under SU2 that I will call delta. It depends on the charge, m. And this is going to be the highest weight. In fact, twice delta is the highest weight of Vm under, so Vm transforms under SU2 is the highest weight of the representation in which Vm transforms. This is very crucial. It's with this delta that we really got the progress in constructing the space of functions. Now, delta depends on the choice of the group and the choice of the representation, which I'll denote by R. In Nakajima's talk, it was denoted by M. By M as a quaternionic representation, and he also used the letter N for describing the complex representation. So we will need to spend some time in order to understand how to compute delta of M as a function of any group that I choose and any representation that I choose. And that's, in fact, a very key point in the construction. So let me quote the result for the case that we are looking at over here. So for our particular case, delta of M is equal to 1/2. This is the basic unit, the basic representation of SU2. There's going to be also a dependence on the magnetic charge. And since delta is always positive, we are going to take the absolute value. And it's also going to be proportional to the number of copies of charge 1 matter fields. Okay, so there's this delta. And now I'm going to look at these functions, Vm. And so delta of M for V is going to be this number. Now I'm missing one more point in the construction, and now I'm going to recall the classical moduli space. There is an R3 over here, and it's parameterized by a parameter which we typically use by the letter phi to denote a scalar field in the adjoint representation of the group. So it's going to be, in this particular case, it's just going to be a triplet of real numbers, but more generally, it's going to be some adjoint value matrix. Okay. Now, since I'm picking a complex structure out of all possible 3, I'm going to divide this phi, which is a triplet, into a complex number and a real number. And in fact, I'll so there's going to be phi c, and it's going to be phi r. This is complex, this is real, and there will be the complex conjugate. But I'm only going to look at holomorphic functions, so I'm just going to forget about these two and only be left with this phi c. And since phi is a triplet under SU2, delta for phi is equal to 1. Okay? Good, and so now I'm about to construct the space of functions. So what can I do in order to get the space of functions? I can get Vm, and I can get any power of phi. And since I'm restricting to holomorphic functions, k is non-negative. And so now this is my space of functions over here. Okay, so m is an integer number, and k is a non-negative integer. And now I'm making the claim that this is the space of functions on this singular space. And how does this come about? I need to identify the way functions are multiplied. So if I take Vm, and let's say that m is positive, this is something that I will not show, but it satisfies the condition that it's just V1 to the positive power, V1 to the m. Right? Since the magnetic charge is conserved, there's only one choice I can take. Right? So I can always replace Vm by V1 to the m. I can do the same thing if m is negative. So let's write it like that. V minus m is V minus 1 to the power m for m positive. Okay? So this defines the way I multiply functions on this space. And you see that I'm here working on a cone, either on the positive cone or on the negative cone, which is parameterized by m. But there is always a question, what happens when I take positive and negative? So if I take v1 times v minus 1, so if it was a classical theory where I don't have this expression, then I will say that this is proportional to the function where m is equal to 0, just like in these cases. However, the delta does not match, right? Because the delta for this guy is going to be half n, and for this guy also is going to be half n. Right, so I cannot write here that the identity will be there. Right? V0 is by definition will be the identity. So it's not consistent to have here the identity. But I do have the other object phi. So from now on, I remove the sub-index c. I'll just call it phi, just like I did over here. And phi has delta equals to 1. So in order to make delta consistent, I'll just put phi to the n. Okay? So now I recovered the condition that those functions satisfy. Okay? So here's the ring structure. Nakajima in his talk talked about a commutative ring, which lives on the Coulomb branch, and this is the way I constructed these rings. Any questions about this?
So your goal is not to try to describe these things metrically, but to describe just the complex structure, right?
Right, and here I should put some bit of history. So people started looking at getting results at such Coulomb branches in 3 dimensions back in mid-90s. And if you look at the series of works back then, the best one could get metrically was on the dimension 1 cases, the rank 1 cases. And that was basically because, well, there were not too many other metrics which existed. And second, there was this uniqueness, right? If you are looking for a ALE space or ALF space, which has a complex dimension 2 and has an SU2 action, there's a classification, and there are so many conditions. You need to do very small checks, and once you do those checks, you get a unique answer. Now, after those set of results, which were derived back in the 90s, there was silence. There was no real progress. I should mention there's something that is called three-dimensional mirror symmetry, which was briefly talked about in the in Nakajima's talk, but mirror symmetry was indirect, right? You need to assume that there is some form of dual theory. And so now, so for years, there was the situation was like this, and the thing was that you know, when I started looking at this problem, I said, okay, people were trying to look for metrics, but what happens if we just relax this thing and not look for metrics? This is too hard. Let's try at least to get the ring structure. Even this was not done over all of these years. And that's how we got into the way we formulate it now. So indeed, the recent progress was in understanding the ring structure. A set of finite generators to the ring and a set of relations that they satisfy. But the next point, perhaps, is to try and look for metrics. But there is a very interesting structure here, which is good for any group and for any representation. So we now have an infinite space of Coulomb branches, which is just waiting to be studied. Okay, so here's the thing, and in order to make the analysis more more manageable, I'm now going to introduce a function h of t. This is called the Hilbert series, which is just going to count holomorphic functions on the space. In fact, it will depend on some other variables, and for this particular case, it's going to depend on two variables, because I remember that m is a conserved number. It's going to now serve as another grading on the space C2 mod Zn. As is well known, C2 mod Zn is toric, and therefore there is a two-dimensional torus action, and Z is going to be parameterizing one of those tori directions, and T is going to parameterize the other. So I'm going to write a function, and it's going to be a sum over all possible numbers that I have, m and k. So m is in Z, and k runs from 0 to infinity. And I'm going to write, take t to be the variable which is conjugate to delta. And to remember that also phi carries delta equals 1. So it's going to add a k over here. And I'm going to keep track of the charge. Okay? So I'm going to have this, and it's easy to sum this up. I'm going to get a function which looks like t to the 2n divided by 1 minus t squared. It's 2k here, sorry. Because I took 2 delta, it's 2k, and 1 minus t to the n times z. Which is nothing but telling me that the space is generated by 3 functions, phi, v1 and v minus 1, subject to a relation of degree to n in t, or of delta equals to n, as we saw over here. Right? So I'm just recovering this relation in the form of this Hilbert series. Okay. Now let's do any questions for this construction for the case of U1 with n flavors. I'm now going to do the case of the other case of rank 1 SU2 with n flavors. And this is, again, the moduli space we anticipate that is going to be C2 mod the discrete group, the helial group of order 4n. And or perhaps it's, let me think. Well, it's, I think it's, there's a shift. Maybe it's 4n plus 4 plus 8. Okay, so, and now, again, I'm going to have the operators Vm, except that here there's something interesting over here. We are dealing with an SU2 group. There is an SU2, there's a U1 subgroup of it, there's a corresponding magnetic charge, but I cannot claim for having a conserved charge, like here. Okay, so there's no conserved charge. However, I can still parameterize those operators, which I called monopole operators, using a magnetic charge M, except that now there is a Weil group action. And it acts on M by taking it to minus itself. Okay? So there's another thing which happens, is that if I, okay, so if I take M as before to be on the line, now it turns out that because of symmetry, of this symmetry, N can be just taken to be only non-negative. Okay? However, there is a distinction here between the point M equals to 0 and M non-zero. Because if M is equal to 0, SE2 is unbroken. And if M is non-zero, SE2 is broken to U1. Okay, so I need to distinguish between those two cases. And that will affect the space of functions that I put on this. In fact, let me just go back to the previous case of C2 mod Zn. Let me characterize the space. So I have this lattice of points M, and on each point I put an operator, Vm, or a function, and on top of these functions I just construct a collection of cones which are generated by phi. So each such cone is phi to the k. And the cone is just parameterized by the values of k. So the space of all functions is just the space of all monopole operators, which are dressed by insertions of phi. So the Coulomb branch, the way I think of it is the space of dressed monopole operators. Okay? Something that in Nakajima's talk was not so emphasized, but the way we think of it like that from physics is as such a space. So now, once I have this understanding, I want to apply it to the case of SU2. And as I made the comment over here, there will be an M equals 0 case and M non-zero, and the dressing factors are going to be different. So different dressing factors. And in fact, if the SU2 is unbroken, I'm going to take phi. Phi is now a complex 2 by 2 matrix. It's in the adjoint representation, so it has a 0 trace. And I can think about invariance. So the only invariant I can come up with is trace phi squared. Now I can, without loss of generality, I'm going to parameterize phi as a diagonal matrix with 2 eigenvalues A, and because of the trace, they just have to be, they sum to 0. So I can replace trace phi squared by just A squared. So the dressing factor is going to be a power of A squared over here. However, when the gauge group is broken down to U1, I can no longer use an invariant which is an invariant of SU2. I'll have to use an invariant of U1. So I'll just use powers of A. So the dressing factor is going to be powers of A. But A transforms under Z2 to minus itself because of the Weil group action. So I have to be very careful. When I dress with powers, I need to take odd powers and not even powers. So let me now specify the space of functions. So I'm going to have Vm. And let me just take the action of the Weil group. So if I have Vm under the Weil group, I'm going to get V minus m. And this is invariant under the Weil group action. That's nice. And I can dress this by trace phi squared to some power, which is again non-negative. That's nice. But what happens when I look at an odd function under the Weil group action? I can also take Vm minus V minus m, but multiply it by A, and again multiply it by trace phi squared to some k. So here you see that the powers of A are even and the powers of A here are odd. So now I'm done. Now I'm done. I characterize all of the functions on this singularity. And again, I could make the analysis. V1, let's look at V1, V minus 1. This is by, and I still did not specify what is delta, so let me write what is delta. Delta of m in this case is going to be, again, it takes this form. The number that I put here is n, so it's going to be n minus 2 times the magnetic charge. Okay? So V1 is going to carry a charge n minus 2. V minus 1 is basically the same operator, so it's also going to carry the charge n minus 2. And so over here, I need to look for a power which looks like 2n minus 4. And so I'll just take trace phi squared to the power n minus 2. Okay? And now, from here, it's very easy to get to the D-type equation. I'll just take V1 plus V1, V minus 1, and I'll call it X. I'll take V1 minus V minus 1 times A, and I'll call this Y. And I'll take A squared. I'll call this Z. And from here, with all of the ingredients that I put, you could check that you get Y squared minus X squared Z equals Z to the n minus 1. So this is the D-type equation. And again, Again, I got the D-type equation just by specifying explicitly the set of functions. Now, I'm going to look at the lattice, as I did over there. How does the lattice look like? Instead of having a magnetic charge which goes over the integers, I have a boundary now. I have the n equals 0 case, and then all of the other cases, and so on. And over here, I have a different cone, a different dressing factor compared with the other cases, which are all the same. Okay? So in terms of functions, in terms of the Hilbert series, what I'm going to do is to write h of t is going to be a sum m from 0 to infinity. I'm going to again get t to the 2 delta of m. And now I'm going to take Pm of phi to, Pm of t to represent the dressing factor. And this dressing factor admits at a different form. Pm is going to be the dressing by trace phi squared if n is equal to 0. And it's going to be the dressing by just phi, or by eigenvalue, for m different than 0. And if I plug these details into the Hilbert series using this form of delta over here, then I will get the Hilbert series of the Dn singularity. And if I remember correctly, it's going to look like 4n minus 4 divided by 1 minus t to the 4th, 1 minus t to the n minus 2n minus 4, and 1 minus t to the 2n minus 2. Okay? Good. So now I'm done with the two rank 1 cases, and I'm ready to characterize this Hilbert series. This is the main result of the talk. I'm going to write down an expression for the Hilbert series for any gauge theory. So in particular, I'm going to apply it to the moduli space of one G2 instanton. And in fact, there's no ADHM construction for one G2 instanton. And this falls under the class of new spaces that I was arguing for over here. So I'm able now to construct the space of holomorphic functions on this space. And the corresponding quiver is going to look like this: 1, 2. And what I'm doing over here is just to take the Dynkin diagram of G2, add an affine node, and use the Dynkin labels, or the Coxeter labels. These are in fact the so-called dual Coxeter labels of the corresponding algebra. Okay?
Now that's the moduli space of one G2 instanton.
It's a natural extension from this case, right? So here what you do is you take the finite A and extend. And the ADHM was already conjectured back in the 90s. So, so if you take the ADE affine quivers, it was already conjectured back then that the moduli space, the Coulomb branch, is the moduli space of one G instanton, where G is any of the ADE type. And this is just an extension of the same idea. Right? So again, what I do is just to take the affine Dynkin diagram. There's also some twisting, but I'm not going to do that. I'm going to take the affine Dynkin diagram, put the dual Coxeter labels, and think of it as a gauge theory. And I just need to explain how do I compute the different functions.
Is there some way of checking it? I mean, one instanton solution in the G2 Yang-Mills theory, one might have thought at least the solution would be available.
Yes, this was known, I guess, going back to Coulomb, but people can correct me that.
Usually for one instanton, the moduli space can be thought of as just the center of mass factor and then some
Coset space.
Coset space group orbit divided by stabilizer, which you could then.
Yes, but as an algebraic manifold, people prefer to think of it as something which is called the minimal nilpotent orbit of the group G.
And one can understand your result in those terms? Or?
Yes, you can compute the set of holomorphic functions on the minimal nilpotent orbit, and you'll just recover it from the formula.
So that's good evidence in support of
Yes. Okay, so now there was in Nakajima's talk there was a question about dual Langlands group. Where does this Langlands group enter? So it enters in this basic observation over there, up there. There is a conserved magnetic charge. So if I have a group G, the set of monopole operators is parameterized by the weight lattice of its Langlands dual, which we will denote by G hat. So it's a very natural object. I just need to take G and to look at the Langlands dual. There is an action of the Weil group. And so if I want to pick just one monopole operator, I'll just divide by the action of the Weil group in order to pick one representative from the whole lattice. So the sums that I was doing in two examples here I divided by the action of the Weil group. Instead of taking M to be running over the integers, I just took half as much. And for the case of U1, there was no need for that. But in general, when I write down the Hilbert series, it's going to be a sum over points in the lattice, let's call it lambda hat, divided by the Weil group. Well, lambda hat is the lattice of the weight lattice lambda. Why do I call it lambda? Well, that's a mistake from gamma.
So what is G hat for G2? The copy of G2?
Yes, it's a copy of G2. Yeah, it's a two-dimensional lattice. You just take the weight lattice of G2.
So rescaled or something?
Not even. I mean, the determinant of the Cartan matrix is 1, and so just G2 itself. However, there's no G2 in this quiver. This quiver has a U1, a U2, and a U1. The nice thing is that the moduli space of G2 instantons doesn't come from a G2 group. The G2 group will arise as the space of global symmetries of this quiver. There's a U1 here, and there is a U1 here, and this will be the Cartan torus of G2.
In terms of the fields of the quiver theory, what does arrow means from 2 to 1?
Right, so I need to explain this. And now I will write down a formula. So let me just finish the expression over here. T twice delta as before. And here I'll have Pm of T. And if it so happens that there is a collection of conserved charge just like we had over there, then I will add Zi, Z1 up to Zk, and I don't know a priori what, well, this is determined by the number of nodes. Z1 to the power M1, Z2 to the power M2, and so on. And I'll have to define what these M1s and MKs are going to be. So let me give you a general expression. So suppose that I have a node and it has rank K. Okay, so I'll label, I will label the node by label I. So here, for example, I give the label 1, and I put in brackets 2 and 3. And so that's going to be the label of the node. And the node has rank Ki. So for rank Ki, I'm going to introduce Ki magnetic charges. So I'll put a label Mi to the node that this corresponds to the node, and I'll put another label, let's call it alpha, where alpha runs from 1 up to Ki. So there will be Ki magnetic charges correspond to the Cartan torus of the corresponding group, and those groups in quiver theories are most of the time unitary groups. Now there is an action of the Weil group. Acts by permutations on all values. So I'm going to fix the action of this Weil group by putting an order. So I'm going to set that Mi1 is greater than Mi2, greater than Mi3, and so on. Greater equal, and Mki. Okay, so that's going to fix the action of the Weil group. And all of these M's are going to enter as points on this big lattice over here. Those M's are going to contribute to delta. And it's going to get contributions from a line so okay, I need to finish. So there's going to be a contribution from lines. So if I have, let's say, this is node I, and this is node J, and there is a line connecting them, so, and there are M alpha I and M alpha J, let's call it beta J, then I'm going to get a contribution which looks like M alpha I minus M J beta, and I need to take the sum over all alpha and beta. Okay, that's going to be a contribution from a line, right? The line connects I and J, and the contribution from the node is going to come with a negative contribution, and so it's only associated to the node I. So it's going to be 1/2 M alpha I minus M beta J. I, sorry, and alpha is less than beta. Sorry, for all, yeah, alpha and less than beta. So if you look at it, this is the set of positive roots of the UK algebra. So I'm going to, since this is a contribution for every node, I'm going to also sum over all nodes. And here I'm going to sum over all lines as well. So I'll just denote it by sum over all lines. And the only thing which is left is to explain what do I do when I have a line that is such a funny line which connects nodes of different lengths. So if I have, so I'm going to put another coefficient, let's call it epsilon. And epsilon is equal to 1 for an ordinary line. or 2 or 3, depending on whether it's a factor of 2 or a factor of 3. For the long root, and the same thing over here. Okay? So as a result, delta gets a very nice interpretation. It gets a contribution from the lines. These are matter fields in the physics language. So it gets a positive contribution from matter fields, and it gets negative contribution from the nodes, from the gauge fields.
Should this epsilon be in the line amount, not the vertex amount?
In the line. Oh, sorry. Thank you. Okay, so here's delta. Now I'm going to describe what is P over here. And I also have to tell what are M, and then I'll be done. So let's do it over here. So P, we saw that for the case of SU2, P had a different contribution from the boundary of the dual lattice and from the bulk of the dual lattice. So this is going to be the same thing again. So PM is going to depend on the cases, and it's going to be the, I'll write it like that, product of 1 I from 1 to n, where, or in this case, I'm going to have a ki, so this is going to be a p per node. And it's going to be 1 minus t to the 2 di, where di is the Casimir, the degree of Casimir invariant of the group GM that is left unbroken. In the background of M. Or in other words, we saw that if M was 0, the surviving group was SU2. If it was non-zero, it's U1. So the degrees of Casimir invariance were either 1 or 2. Over here, I mean, if I'll pick a partition of Ki, so it's going to be some j and j. Then the residual group is going to be product of u and I and j. And then there will be a collection of Casimir invariants. It all happens at the boundaries of the Weil chamber, where in this ordering that we have over here, some of these magnetic charges become equal. So whenever some of them become equal, the residual group is changing, and we have to put different dressing factors. Okay, so let me summarize. Now, if you repeat this thing, if you plug the data into this quiver, so it's not so bad. In this case, we have a U1 gauge theory, U2, U1. There is a special edge over here, another edge over here. So you plug those two into the formula for delta. The lattice of U1 is trivial. and the lattice of U2 is just a two-dimensional lattice. It looks like a triangle. If I set this condition, so it's a very simple sum, and you get that the Hilbert series is let me write the final answer. It's just the well, this is the character of the representation of G2 with highest weight n times the highest weight of the adjoint representation. So theta is the highest weight for the adjoint representation, and n times theta is just n times this highest weight. Okay. Now I did not mention these m's. These m's are fairly simple. M1 is just, so mi is just the sum over alpha m alpha I, like that. It's a simple number. It's just the overall U1 of the group UN. Okay, so to your question, where does G2 arise? So once I keep track of the magnetic charges of this node and of this node, I will get that this gives me a weight on the root lattice of G2 corresponding to the fundamental root, and M1 plus M2 for this node will give me the weight of the root lattice of G2 for corresponding to the adjoint root. Okay, so here's the formula. Let me make some concluding remarks. So we have this formula. This is called the monopole formula, and it's quite promising because using this I can construct algebraic commutative rings for spaces given for any quiver. I can take any gauge group and any matter, any representation, and plug it into this formula. It's an explicit formula that constructs the or counts functions on the ring of functions on the of the hyperkähler space, and the reason it's very promising is because now I can start looking for various properties of these things. So Nakajima already presented some quantizations of these moduli spaces, and it's first time we could get a handle on the algebraic structure of moduli space of K G instantons where G is exceptional, and I'm sure we can find many other examples and many other uses for that. So thank you for listening.
Question?
So in general, is there a presentation of the ring, or is it just the Hilbert series that you've got?
It's the Hilbert series, and there is always an issue once you have a Hilbert series. Can you extract the space of the set of generators of the ring? Since it's finite dimensional, it has to be finite number of generators of the ring, and you could use combinatorial techniques in order to identify the generator. So for all of the cases that we studied, we were able to do that. But as a general theorem, I am not aware of any theorem that given a Hilbert series, you can construct the space of the ring of functions. So the Hilbert series can do a reduction of the problem by saying, so it can tell you what are the degrees of the relations, and it can tell you what are the degrees of the generators. And so you could go back to the space of functions and actually construct them. And when you deal with relations, you could get to a situation where you have, using those space functions, you can construct, let's say, several functions which have the same degree as the relation. So let's call them OI. And the best I can say is that the relation will come with a collection of coefficients, numerical coefficients AI, and they sum to 0. So it reduces the problem to identifying this set of numbers which come in front. Okay, so that's the best the Hilbert series can do. In many cases, we are able to reduce those numbers into zeros and ones.
In the example, is it easy to get the Poisson bracket as well, or is it just the function?
There are cases. So, for example, Nick is looking at some limits where the ranks go to infinity. And in those cases, there is some notion of a Poisson bracket. But I haven't looked at the details, so I'm not sure. I mean, but this falls under the wonderful set of generalizations that you could do with this formula.
So this G2 instanton example, that was the Coulomb branch of a theory, right?
Yes, the Coulomb branch of this.
Branch.
So
the Higgs branch in that case?
I don't have a good notion of a Higgs branch for theories where the quiver is not simply laced. However, you seem to have an idea. So yeah, so Higgs branches I can only understand when the edges are regular edges.
What was the dimension of the Moduli space?
It's the dual Coxeter number of G2. So it's in this case the complex dimension is 3 times 2. So it's always the dimension of the moduli space of k G instantons on C2, or you would like to call it tau naught. It's going to be equal to, this is the complex dimension, 2 times the instanton number times the dual Coxeter number of the group G, and you could either take the center of positions or not, right? So you could either subtract 1 or not. So this is with the center.
Is it known what dimension the Higgs branch is supposed to be?
So for the affine, for the simply laced guys, in fact, this is.
Sure, but no, the question that came after.
It's so if you take this, then you know, going back to the work of Kronheimer, if you put ranks k over here, and
no, in the case that Tamak is asking.
which case?
In the case that Tamak is asking for this non.
No, I don't know what is a Higgs branch, not even for the one case. But it's just going to be the Hilbert scheme of k points of d-type singularities. And so that's the Higgs branch, and the Coulomb branch is going to be the moduli space of k, d-type instantons, and so on.
Additional question?
Yes.
So there is no Lagrangian description for this?
This one I can give you cases for, let's take the affine B. So the affine B is going to look like this with ranks 1, 2, 2, 1, and you could multiply it by k and extend.
Okay.
And now for this, to translate your question to string theory or to brane physics, for this I do have a brane description. And I can try to guess what is the gauge theory on this particular edge.
So do you have field theoretic description just in terms of the vector map?
Possibly some boundary conditions on the path integral that you should put. However, it was never formulated in a proper way. I mean, so it looks like.
So for this quiver with the G2, that rule about epsilon is just a rule about counting of the dimensions of monopole operator. You
That's
don't
right.
have field theoretical description for
That's
theory,
true.
like in terms of the gauge group and representation.
That's true.
Additional question? Let's thank the speaker again.
Thank you.